Before I start flipping slides and doing lectures, I just want to stop for a minute and welcome everyone to these lectures on foundations. I want to welcome both my students at University of Tennessee at Chattanooga who have taken these for a long time. I'll tell you how long in a minute. And for those of you who are just coming and watching these, welcome. Thank you for your patience. Thank you for your interest in the topic. I've been teaching foundations in soil mechanics at University of Tennessee at Chattanooga since 2001, and I actually taught this course for the first time in the spring of 2002. And I've been teaching them on a consistent basis since the fall of 2009. And when I did this, I've always had it in mind, and one of the reasons why I developed my website the way I've done it over the years is to reach out to a broader audience. I've been in the industry a long time. I started with my family business, which makes pile driving equipment, in 1978 on a full-time basis. My family has been in this business since the 1880s when we developed the Warrington Vulcan style hammers. We've been around here a long time, and I've come from a little bit different perspective than many people who teach this course and many academics. So I wanted to share that perspective in a course that would be kind of drawn from that, and of course from the basic science and engineering of foundations. The COVID-19 crisis has given me the opportunity to actually put this thing on, or actually maybe I ought to rephrase that. It's actually just forced me and many other academics to put stuff online that they wouldn't otherwise have done. So I know this is difficult for my students who came for a face-to-face experience. I'll try in these lectures, as I've done with some of my other course, to within the confines of this studio you see around me, so to speak, and in terms of the other things, to give something which is as close to what I actually do in class as possible, and at the same time to do things which you can't do in class easily. I'll eliminate a lot of the shuffling around I've done over the years with videos and that kind of thing. So my intent is to give you the best possible experience possible for this course and to convey the information, and also, but most importantly of all, engineering education is about mind development and teaching people how to think. And over the years, I've seen deficiencies in that in the field. And one of the reasons why I teach the course the way I do is to correct those deficiencies. So, welcome. This has not been an easy transition for anybody, but with God's help, we're going to make this the best we can. So, let's proceed to our topic. Our topic is, in fact, foundation analysis and design. I want to tell a little story. I was intermittent in my teaching at UTC throughout most of the first decade of this millennium, and I worked, among other things, as the webmaster for the Church of God Chaplains Commission, which endorses chaplains for things like the military, prisons, hospitals, and that sort of thing. It's a fascinating field. It involves a lot of what people in the social sciences call clinical applications. And his director was a man named Dr. Robert Crick, an former Army chaplain, and himself very versed in the clinical part of this. And he asked me one day, "What course are you teaching?" I said, "Well, I'm just teaching foundations." He says, "Foundations of what?" Well, in academics, there are many courses that call themselves foundations of this, foundations of that, but this is the foundations course. And the foundations course, I wouldn't say the rest of them are based, but these are the foundations after which the other foundations are kind of modeled after. So this is the ultimate foundations course, in my opinion. So let's proceed. We have two textbooks, which I use in this course. The first one is this one, which is the Soils and Foundations Reference Manual, or I sometimes call it the Soils and Foundations Handbook. It was produced by the FHWA back in the late 70s, early 80s. It was first produced to teach people in departments of transportation the basics of geotechnical engineering. It is a very practical course. There are certain things where it does not cover very well that I think engineers need to know, and I'm going to explain how I supplement that in just a second. But for practical, real-life engineering, it's an excellent reference, and I think you will find it easy to read and easy to understand. The second one is this one, which Soil Mechanics by Arnold Verrooyd. In a report that Arcadis commissioned, and both Arcadis and Verrooyd are Dutch, is one of the individual who wrote the report said they consulted with Verrooyd, and Verrooyd was the kind of person that made the complex simple. And in many ways, Verrooyd's very good at that, although sometimes he presupposes a level of math education that we just don't have in the United States. But for the more theoretical parts, and there are certain other aspects which the Soils and Foundations reference manual doesn't cover, we have Verrooyd. I also have the slides. Most of my students, ever since I've started to teach this, have used the slides as sort of a substitute textbook. In certain parts of the course, that's exactly what it is. I try to, one of the nice things about using public domain or freely available material like this is that I can actually copy and paste that into the slides. I'm using the slides as sort of, this is where I am in the book. This is where you need to be in the book, or whatever book I'm using. Sometimes I'll diverge from the book, in which case the slides become a textbook. The other thing, advantage about the openly available textbooks, is that both of them are found online as well as in print. So there's no need to spend a lot of money. And this comes from a textbook author, a published textbook author. So with that in mind, the other thing, I have some credits over here. The slides, I tried several things to figure out the best way. This kind of replicates what I do in class for my face-to-face classes, where we've got a screen and slides and me. And I got several ideas using video editing, and this is what I basically came up with. I hope it works. If you can't read the slides that you see over here, then the slides are available in PDF format to download and read. And if you like, print them out if you insist on it. So, I also have some line drawing credits, people and organizations who have contributed either directly or indirectly their material to this course. And I've showed them over there. And I appreciate their contribution very, very much. What we need from soil mechanics. Soil mechanics and foundations are kind of the same relation as Luke and the Acts have in the New Testament. One is the prequel of the other, or the other is the sequel of the one. This is the sequel to soil mechanics, and we need certain things from soil mechanics that we that you need to be familiar with. This is first of all, the most important thing, single thing, happens to be phase relationships. And by the way, some people who teach this course do a 2 or 3 week review of soil mechanics. The only topic I'm going to actually go over again is lateral earth pressures. And this seems to be one of the most difficult subjects students have to grasp. But in any event, that taken out, there are some things you need to be aware of and need to remember. Phase relationships, water, air, volume. These are inescapable for granular material. You will be using these again. Total stresses, effective stresses, and pore water pressure. These are also very important, especially when we get into deep foundations and to a similar extent to lateral earth pressures. You need to understand these well. Most of what we do in foundations assumes hydrostatic conditions, which simplifies things. Consolidation and volume change due to particle rearrangement and pore water squeeze. This is important for settlement. I'm not going to go over again we're going to learn some more methods for settlement for mostly granular, mostly for cohesionless soils. There will be some reference back to the cohesive soil stuff, so be prepared. And of course, lateral earth pressures. My general approach to foundation design is to basically we start by examining the site, finding out what the site is all about, its geology, any major pitfalls in that geology. Sometimes those are literal pitfalls, and particularly with karst topography. After that, you take and you look at the structure that you're trying to put on these and see how they interact. There are certain situations where you actually have to modify the structure that you do to suit the soil conditions. An example of that, what should have happened, was I had an Algerian lab assistant a few years back for soil mechanics lab, and she told me about a mosque that the government wanted to build right in the middle of Algiers. Now, Algeria is a seismically active region, and the soils in that part of the town are usually soft. That's usually a recipe for disaster, especially if you've got a major structure. And from what I understand, this mosque they wanted to put in, it's probably been built as a honker. But they had no regard for the basic geology, and so they end up spending a lot of extra money. That can be avoided if both the engineers and the owners recognize the fact that there are some times when it's necessary to tailor the structure desired to the geology. And of course, your selection of foundations will be based on the geology as well. I mean, that's a must. We're going to talk about that with every type of foundation and lateral earth structure we deal with in this course. How does it interface with the geology? How does that influence our selection of a foundation type? Will certain foundations do better in certain geologies than others? Even if there's, for example, both deep foundations. Deep foundations, you have certain geologies where driven piles are the thing. There are certain geologies where you're better off with drill shafts. As much as I hate to admit it, it's the truth. And then you've got other things. So, and then you how to implement it. Is this foundation I've designed constructible? Is it economical? Does it do the job that it's intended to do? All of these things go into account when you're actually designing foundations. It's not just, we take this, we make these calculations, and we throw them out at the structure, to finish the design, and we're done. You can't blindly do a foundation that way. You can't do any foundation that way. You have to think about the environment it's going into. All right. Requirements for the basic requirements, we have two things. There are four things. Now, I've kind of touched on some of them. Strength requirements. Is the foundation strong enough? Will it fail? And it's not just the structure. You've got two types of design we deal with foundations. One of them is the geotechnical design. Will the soils fail? And the second is the structural design. Will the structure itself fail? Will the pile fail? Will the wall fail? Now, one of the interesting twists about this course is that as a result of what I experienced last year, I decided it was time to do a house cleaning and rearrangement of this course. And as a result of that, there are some topics which I've taught for many years have been eliminated, and some others which I've picked up. The one major consequence of that is that we have almost entirely eliminated the structural component of the course. In other words, the failure of the structures, bending moment, axial failure, that kind of thing, with one important exception, have been pretty much eliminated from the course. And the one important exception is sheet piling. And we'll see how that works out when we get to it. But all we're going to focus on is the geotechnical failure. Some of the structural aspects of deep foundations are very similar to those in the surface. For example, drill shafts. Drill shafts are basically a concrete column, and they can be designed as a concrete column with certain modifications. The design is very similar. So, and with shallow foundations, they are basically concrete slabs, reinforced concrete slabs. So both of those can be designed with a basic understanding of what you learn in your concrete courses. I don't see going over it again. We have more important things to cover in the time that we're allotted for this. A strength requirement, getting back to the slides, I get off the subject quite a bit. Getting back to the slides, a strength requirement is a requirement where to keep the foundation from failing catastrophically. And catastrophic failure, in soil mechanics, we talked about slope stability as a catastrophic failure. We also talked about lateral earth pressure. These are failures usually along a failure surface in the soil, and they tend to be catastrophic. Serviceability requirements primarily mean settlement and movement of the structure under load. I don't, traditionally we've designed, the codes are set up this way, the pedagogy of this course is set up this way, and to differentiate these very clearly. But just between us chickens, a lot of real design, you can't split it up that easily. That's particularly true with deep foundations. You really cannot. You always are going to, most all of the design, particularly with deep foundations, is based on deflection, excessive deflection. And the two interact with each other. There are some foundations that are, like deep foundations particularly, that are more prone to serviceability, to a deflection failure, settlement type failure, than they are a strength, or failure, catastrophic failure of the soil. So the two, particularly if you once you get into finite elements, and you're able to combine the elastic region, and we talked about this in soil mechanics as well, the elastic region and the plastic region, and you can analyze them in one shot, you begin to realize that actually stuff usually moves a little bit maybe, but before it actually fails. You've also talked about constructability requirements and economic requirements. That was the kind of the deal with the mosque in Algiers. It was, you can do it, but it's expensive. It depends how much money you have to spend. You have to talk about the types of loads on foundations, the sources of those loads. That can frequently influence what foundation you have. Example, deep foundations are much better at lateral loads than shallow foundations. For reasons that will become obvious, that may influence whether you pick one or the other. A structure that otherwise would be just the bomb with a shallow foundation needs lateral load support. And there's more than one way to do that too. There are other questions. How do we consider with uncertainty? We'll talk about that, particularly with LRFD. If there's one thing that I think that this whole COVID-19 thing is brought to the forefront, is the fact that science has uncertainties. And and in geotechnical engineering, we live with those uncertainties all the time. So you have to deal with them. You have to adapt a mindset. And a lot of engineering education gives an air of exactitude, which in reality is not justified. The environment is too complex to, even if you've got using advanced analysis tools, the environment is too complex to ascribe exactitude or precision to an analysis. And that's something you need to keep in mind. And we're talking about uncertainty, particularly LRFD, because that was actually based on a probabilistic. Actually, I'm going to talk about, let me get to that. That's another subject. Combined loads. We're not going to spend a lot of time on combined loads. It's an important topic, and LRFD does a little bit better job than ASD to quantify that. But I think an introductory course to spend a lot of time on combined loads will get us off the subject. We have more important things to cover. The code environment. Just a reminder to everybody. Just because you've designed something to code doesn't mean you've designed it right. Keep that in mind. It may be the code, but it may not be right. And finally, how do different foundations, different loading? And that kind of goes back to some of the stuff I've already talked about. Sources of loading. There are many different sources of loading. We have most of the classic loading is axial loading. But bridges and other structures are subject to all kinds of loading, both in all kinds of different directions. Some loading is constant, like a dead load. Some constant will vary some, like your live loads. Some are what I would call occasional loads, although sometimes I'm beginning to wonder some of what we thought was occasional has become more routine, such as high wind loads, water loads, earthquake loads, and that sort of thing. So the frequency of those loads will and their severity will influence how much we take those into consideration in design. We don't necessarily want to design a structure for the absolute, we want to take into consideration all the loads, but an occasional load would get, say, less of our consideration than something that's there all the time. And LRFD is also good at quantifying stuff like that. Two types of loads that are very important to consider. We'll consider there's lateral loading, which you see a lot of with bridges have some lateral loading. Lateral loading, particularly, of course, for earth retaining structures, lateral loading is pretty much what you've got. Uplift loading. That particular photo in the slides is an earthquake remediation out in Memphis. So there are, both of these types of loadings, both of which can take place during seismic events, are things you have to consider. You have to consider, when you're dealing with a source of information. Many times when you're looking at a site, and I'm actually, one of the things that I've changed this go around is I'm going to spend more time on boring logs, site plans, and that sort of things. I think this is something that gets the short shrift in most foundations courses, but if you're going to either go into geotechnical engineering or you're going to be involved with this type of design, you've got to understand boring logs and site surveys. You can always use when in dealing with design of the past and experience in the past. Past experience can be very useful. It can save you a lot of mistakes. Sometimes it's constraining. Sometimes we've always done it this way will hold you back from economical solutions, but never discount it completely. Never. You need to consider it. You may not do it that way, but it needs to be in your game plan to actually consider and either adopt it, partially or totally, or reject it for a good reason. I would not reject something done in the past just because. Now there are some situations where stuff in the past has problems, and you need to learn from those problems instead of just repeating them. The more information you can get, the better. Some job sites, plans I've looked at have both the current plan for the job, and the current borings and whatnot, and also those from many years ago. Both of these sets of information can be very useful. The more information you have, the better. I'll get to that in a minute. So you have to consider all of these things, and we've talked about those considerations already. There are many methods of analysis. We've talked about those in soil mechanics. We're going to do this again. Like I said, I've created an entire section on this subject, and towards the end of the course, we're going to look at this. I think it's important. I think you'll find it interesting. We have all kinds of, looking over here, you've got your seismic or your geophysical methods, which can be very useful. You have classical site boring. Some people ask me, do you think that geophysical methods will ever displace site borings? The answer is no. They won't. There will always be a need for some borings. To use the ideal situation is to use the two together. Because geophysical you can get a lot of information with not much effort, and then you can spread it out. Then you can use your borings to really pinpoint places and really get more information. So the two together are ideal. You've got all kinds of probe tests. You've got CPT, your cone penetrometer test, your SPT, standard penetration test, which is very common and still in the United States. Many, a lot of the current books and whatnot want to get away from SPT. If you're going to be looking at soil borings, either current or historical, you better be prepared to know what SPT is all about. Test pits for shallow foundations. Obviously, test pits are the way to do it. You've got other different, your Marchetti and Menard testers, which are very interesting. And of course, finally, you've got plate load test. And we're going to talk about those some. Those are particularly useful for pavements, although pavements have advanced and there are quite a few different ways of testing for soil specifically for pavements, most of which I will not get into in this course. Many people will tell you that the more testing, the merrier, but your clients kind of know different. There is that optimum point, and I've shown this. This actually goes back almost 40 years. There's an optimum point at which the intensity of the site investigation becomes too much. There is a point where you've got just enough site investigation to produce the best possible design. If you go less than that, then you end up having to fudge the design and hope that your fudging gets the job done. If you have too much, then the expense of the testing starts to outweigh the benefits. That sweet spot is always hard to find. You will discover in practical life that most job sites are on the left side of the sweet spot. They're towards the less testing. Generally speaking, it's a very rare job site that they've done too much. But your objective is to try to get to that sweet spot of testing. We're going to talk about several types of foundations in this. We talk about spread footings. We talk about mat or raft foundations. We're not going to do a lot on mat foundations. They're fairly complicated analysis. Spread footings is going to be our main focus for shallow foundations. And by the way, every video starts with a splash screen. And that splash screen is a photo of the Engineering, Math, and Computer Science building when it was being built back in 2002. It's on spread footings, and that's the first thing we're going to deal with. For deep foundations, we have driven piles, drill shafts, auger cast piles. Floating foundations, I'm not going to spend too much time. We're going to talk about floating things under the soil. This is one place where I've made some fairly substantial changes in the way this course is taught. And lateral structures, gravity walls, sheet piling, reinforced. We're going to talk about those as well. Math foundations can be very, I honestly think today that there are a lot of many things that we can still design using what I traditionally call closed form. In foundations, empirical is usually a better way. Empirical methods or formula methods maybe is the best way to put them. A closed form solution assumes a better theoretical basis than a lot of foundation methods actually have, even now. Math foundations is one, we've gotten into finite elements. I really feel for any size of mat that a finite element analysis is really what it's called for. And because you've got basically an elastic, you're basically putting a flexible foundation and a flexible structure on an elastoplastic medium, a medium that deforms. Everything is deforming all at once and interacts with each other. So I normally don't spend a lot of time anymore on mats, and a lot of that part of the course is different from what you've had in the past. I've taught in the past. Deep foundations, driven piles, which is what I've been involved with most of my career, but we also have drill shafts. Those are the two main types of deep foundations. We'll talk some about auger cast piles and other types of things. We got micro piles. There's all kinds of deep foundations, many of which are proprietary. I can't cover everything. I will cover the basics of these foundations. One thing that always complicates life in soil mechanics is groundwater. Groundwater is the thing that really makes things very complicated. If it wasn't for groundwater, I think geotechnical engineering would be very simple, but we'd all be dead. So you got to take the good with the bad. And of course, changes in groundwater. Groundwater is not static. It goes up and down. And as a result of that going up and down, it can change foundation. You have to design a foundation for varying groundwater conditions. Otherwise, you're going to have problems. This is particularly nasty when you get into expansive soils, which we'll talk about in this course. Expansive soils basically change their volume substantially with changes in water content. They swell and shrink. And as a result, you have to and if you don't design for changes in water table levels, your foundation is going to be a mess. Groundwater, neighboring structures. Neighboring structures are very important to consider with your with a foundation, particularly in urban areas and in tight places. This has been more of an issue in Europe than it's been in the United States and in Asia as well, because you've got more crowded conditions. In the U.S., we've traditionally had more room to spread out, but these are things which one must consider with many projects. What effect will, for example, putting a foundation in one structure affect that which is next to it? In some cases it does. One of the things that we don't spend a lot of time thinking about is the definition of failure. Jerry Leonard's from Purdue put it this way: an unacceptable difference between expected and observed performance. That's kind of an understatement, but that pretty much sums it up. With a catastrophic failure, that difference is very stark. With strength failure, with a serviceability or settlement failure, that's a little more subtle. It's a broad, and a broad definition is called for in this case. There are also other factors for failure as well, the type of structure and whatnot. These things can influence how it fails. For example, with shallow foundation, we can talk about the catastrophic failure of bearing capacity failure, where it fails along a surface, and you see the surface in the diagram on the left, where you have those failure surfaces is where basically the foundation turns over. It's very similar to slope stability failure. On the right, you look at something failed during settlement. And the fun thing about settlement is that not only can an entire building sink, but at the same time, parts of a building can sink more than others. Settle more. That's called differential settlement. That's especially nasty because if you've got a severe differential spot, you can create distress in a structure that can make it unusable. Those of you who've cruised around camp, kind of appealing to, particularly in this area of East Tennessee, who see the little cracks in the masonry, the little stair-step cracks in the masonry, 9 times out of 10 you're looking at differential failure. One part of the structure is settled and one hasn't. And it can be, actually, it can be very destructive. With retaining walls, most of those failures are catastrophic when they happen. Some are not. Basically, on the soil, you've got basically a soil side of the wall, and you've got what I traditionally call the dredge line, or the dredge side of the soil, where the soil is lower. And generally speaking, most of the soil movement is in active pressures on the soil side and passive pressures on the dredge side. That means you'll have to excuse my marine kind of view of things. Generally speaking, for most types of retaining walls, we ignore what's going on in the passive zone. Sheet piling is a notable exception to that, for reasons which will become obvious. In cases where the balancing soils or the weight of the wall, such as a gravity wall, isn't enough to keep the wall in place, we use anchors. This is an example using an anchored sheet pile wall. We also have brace cuts. Brace cuts, and we talked about those in soil mechanics. Brace cuts are basically 2 sets, usually sheeting. You don't have to be, but they can be other types of walls. You do slurry cutoffs and that sort of thing. You can have those as well, where you basically want to create a reinforced ditch in the ground. The simplest form of reinforced ditch are your trench boxes, which you see to prevent cave-in for relatively shallow work. For deeper work, you use a brace cuts. In shoal mechanics, we talked about the issue of keeping one dry. In this one, we're going to talk about it keeping it upright. Another very interesting way of reinforcing walls are your MSC walls. And I'll just be real honest with you, I have not seen a really good treatment. I'm going to do the best I can with this topic, but I have not seen a very good treatment of MSC walls in the literature, as far in textbooks or whatnot, as far as designing them. We're going to try to keep it simple as possible, but MSC walls are surprisingly complicated, but they're very important. You see them much more in transportation projects than you did years ago. It is a very economical way of reinforcing a wall, and some of them can be very tall as well. And then sometimes we have projects which don't know what they want to do when they grow up. We have combined types. We have retaining walls, pile supported retaining walls. We have retaining walls. The gravity walls are almost exclusively, are almost inevitably either are can be shallow foundations at the base, or they can be supported by piles or whatever. So we've got where these situations combine themselves. How have we analyzed this stuff? Historically, we've been designing and building buildings long before we established a theoretical basis to do so. And many of these structures have outlasted the stuff that we've built with the science. So therefore, we have to consider, and we were that limited us, but many of these structures are very durable, and we've learned a lot. Really, geotechnical engineering was a purely empirical type of thing up to about the beginning of the 20th century, or a little bit before that. People started to look at it differently. But up to about the beginning of the 20th century, it's purely empirical. A lot of attention is given to Terzaghi, justifiably so, with his consolidation theory and all the other things. He did many. His work touched on many different topics. But there were other things that were actually the theory of elasticity solutions we talked about in soil mechanics, slope stability predates Terzaghi. So for that matter, permeability predates Terzaghi. So many of these things were already in the works, so to speak, when he came along. But his contributions changed foundations in soil mechanics forever. It wasn't, but we've always been kind of the laggard. The uncertainties in design and in the environment have always made geotechs more conservative, just by any other civil discipline. And as a result, the introduction of computer-based applications, and we're talking about some of those in this course, have always been a step behind. The adoption of LRFD was a step behind, although I've got one colleague who feels that they should never adopt it at all, but that's a different topic altogether. The use of finite elements is still not entirely accepted. One reason I think why it isn't is because it's more difficult to verify whether someone has done their work properly or not when they're just looking at a lot of computer output, which is why many organizations, your DOTs and whatnot, need some, prefer to use your formula type methods. Personally, I think that there are situations where formula type methods are just about as good given the information you have. The ideal situation is to have something where you can do justification based on both formula type methods and on finite element analysis. Expression of design load. We're going to talk about two of these. This is sort of the end of the course thing. Until the end of the course, I'm going to stick with ASD, allowable stress design, for all of this course. The reason for that is very simple. I feel that if you introduce LRFD, which is fairly complex in its implementation, if you introduce LRFD at the same time you're trying to teach people about the physics, you're going to have a confusing mess in your hands. I think ASD is easier to incorporate into the physics. It will be at the end of the course when we'll actually shift from strictly ASD to LRFD. And I'll talk about some of that when we get there. There's no sense in going over it twice. These are some suggested factors of safety. They're not written in stone. You're going to see a lot more of this before it's over with. Load and resistance design is based on a probability. It's an attempt to enable engineers to do a probabilistic analysis without getting lost in the statistics, and actually to have a lot of these statistical capabilities built in for them. So that's pretty much it with LRFD. Like I said, I don't think I think it's something which has been adopted for most design in the U.S. It's, again, keep in mind, it's been pushed very hard by organizations such as AASHTO and FHWA. That doesn't necessarily mean that the organization you're designing this thing for, whatever you're designing, actually accepts that. So that's another reason why I do it both ways. We're going to talk about that later. Once you get to designing, you need to verify. Verification is essential in proper geotechnical design. You just can't design it and walk away from it. It helps. You need to have that's for the very simplest of structures. You need to have some way of verifying it. And so that's particularly true with deep foundations. Verification is a must of some kind because your soil conditions are too variable. And so we have things like, and you see there an example of static load testing. And we're going to deal with that as well. Codes as I said, codes are important. Every structure around is designed in some kind of code environment, and that code environment must be adhered to if the structure is to be acceptable. The problem is, again, I'll say this again, just because a structure is designed according to code doesn't mean that it's necessarily properly engineered. Adherence to a code is never a substitute for proper engineering judgment. Constructability. Engineers, particularly, the problem we've had, it used to be, and I said it used to be a long, long time ago, that most engineers had some experience in construction. Today, that's not the case. Many times they are asked to design projects and they don't really, with a really poor or non-existent understanding of how it's built. That's not good. But that's an inevitable result of the specialization that we have in life in general these days. Any engineer who wants to be really proficient at design must understand constructability. There is no sense in designing a structure that cannot be built. None. So it's important for you as an engineer to understand some aspects of constructability. I'm going to try to emphasize those in this course, but it won't be the in other words, I can't do everything. There's a lot more to learn after this is done for. And those of you who are experienced designers listen to this say, will second me on that. So make sure that your constructability, you can build it. And not only that, but many times it's a temptation to try new methods. New methods are important. It's good to advance it. I think the best way of implementing a new method is to use pilot projects and that sort of thing. To take an ordinary project and try to do something on a major basic scale that way is risky. And we'll end up with the problem is the biggest manifestation is the expense will go through the roof. So that's my introduction to foundations. We're going to start with shallow foundations. In the meantime, see you then. Thanks for watching, and God bless.